Here we have section 4.3, and now we want to look at some of the properties of definite integrals. Now remember, they're just sums and limits of sums, definite integrals. Okay, so one of the first properties is that as long as f is defined there, so f of a defined, that's kind of like the continuity part, then the integral from a to a of f of x dx is 0. Now, that makes sense in that, remember, this is a sum and we had to multiply by delta x. Well, there is no width here, right? Delta x would have to be 0. And so we're taking the function value times 0, we get 0. And so that one seems pretty reasonable. And then the other one is, as long as this integral existed to begin with, the integral from b to a of f of x dx is defined to be, and these are definitions, okay, so it's not really, again, this definition makes sense because delta x would need to be 0, but trying to set up that limit and so forth would be weird, right? And so we just define things this way. And then similarly, we define that if we change the limits of integration in essence to go backward, then we just get the negative of what we had before. And that in some ways sort of makes sense, just again from the delta x point of view, that if we're counting backwards, maybe you'd count that width as a negative, but it's kind of weird. But that's why these are definitions. Okay, they're not theorems to be proved. We just say this is the way it is. And so, for instance, if I have the integral, they give this example from 3 to 0 of x plus 2 dx. Well, what is that? Well, it's the negative of the integral from 0 to 3 of x plus 2 dx. And we already did this. This was the trapezoid. And in this trapezoid, we got 21 over 2. So this answer is negative 21 over 2. This was in the previous video, the 21 over 2 with example 3b. And so we get just that negative. So, okay. Now, more properties, additive or subtractive. Additive property is that if we split up the interval, so here's an interval from a to b of f of x dx, that is the same as the integral from a to c, that's a c, of f of x dx, and plus the integral from c to b of f of x dx. Now c does not actually have to be between a and b to make this work because of this negative property up here, but if it is, if you're thinking of something like this, and here's a, here's b, and we did this integral which we could think of as area, well then pick some c in here and find that, and find that, well, sure, they should add to the total area of A and B. Now, if C is actually bigger, say, than B, and we went from A to B like that, so, here's A, here's B, and then C's down here, well, sort of what happens? Well, when we go from A to C, we get that whole area, but then notice when we go from C to B, we get the negative of that area, and so we end up subtracting it off, and we get back to just that area there. So it works whether C is in between A and B or not. And let's see, our final couple properties. So we had that additive property, then we have a scalar multiple property. So if I have A to be of some constant k times f of x dx, well, remember it's a sum, and then the limit of a sum. Well, we can factor the k out of the sum, and we can factor the k out of the limit, and so this is k times the integral from a to b of f of x dx. Okay, so there's another property. I guess we're up to property number 4. I don't think I put a number on this one. Property number 3. And then finally property 5, another additive property, but this time it's of the stuff that's inside. So f of x plus or minus g of x dx. Then this says, oh, we can split that into two separate definite integrals, f of x dx, and then plus or minus, depending on what we had there, the integral from a to b of g of x dx. And again, this one is reasonable in that you can look at the f of x plus g of x. A way to interpret that, now it's not really quite what's going on, but a way to interpret that is, suppose this is f and that's g, and I think of the subtraction, then f minus g is this stuff. Here's a and here's b. F minus g is sort of these heights in here, right? And so we're making our rectangles out of that, and we would find that area. Over here, you see we're finding the whole area from f to the x-axis, and here we're finding the whole area from g to the x-axis, and if we're doing a subtraction, then we would take that whole big area, subtract off that, and we get this up here. So it seems reasonable. So again, now by definition, when you do the f of x minus g of x, you're not actually dealing with this area up here. What you've done is you've created a new function, h equal f minus g, and here's a, here's b. You've created that height and you found this area, but that area is the same as that area. Okay, so those are our properties. Oh, we do have a couple more. I almost forgot to put those in. We have inequalities as well. So if f of x is greater than or equal to 0 on AB and it's integrable, in other words, it's continuous on AB, then 0 is less than or equal to the integral from a to b of f of x dx. And again, that makes sense because what we're doing is adding up values of f times the delta x, where the delta x is always positive. So I'm adding up positive values. That's the thing to remember about this thing, is it's a sum, right? And so if f of x is non-negative, then I'm just adding up a bunch of things that are non-negative, mostly positive probably. And so if I add up a bunch of positive numbers, well, I can only get a positive result. Now, it's possible, I guess, I could be adding a bunch of zeros and get zero, so the equal to part. But if I'm just adding up a bunch of non-negative numbers, I should get a non-negative answer. So that makes sense. And then if, similarly, if f of x is less than or equal to g of x on AB everywhere, then the integral of f of x dx from a to b has to be less than the integral from a to b of g of x dx. And of course here, you can think of it as just adding, right? I'm adding up a bunch of things like this and a bunch of things like that. Well, these over here on the right are always bigger, so when I add them up, I should get a bigger answer. But also in terms of area, right? Here's g of x, there's f of x, and when I look at those areas, if f is always down here, its area should be less than that big area with g of x. Okay, so that's all our properties that they give. It is absolutely worth making sure you get those and understand those. It makes life much easier because, again, you can get some intuition from looking at graphs and just knowing some of these basic inequalities and properties.